We're diving into locally linear embedding, a powerful technique in machine learning for reducing the dimensions of data. A key parameter in LLE is n_neighbors. Think of it as deciding how many neighboring data points we consider when trying to understand a single data point. This is a multiple-choice question designed to test your understanding of the n_neighbors parameter within the LLE algorithm. It's all about understanding how this parameter affects the algorithm's results. Get ready to put your knowledge to the test. This question asks you to identify the correct statements about the n_neighbors parameter from the given choices. Each choice describes how the n_neighbors parameter might impact computation and LLE results. Let's analyze each statement carefully. I agree that this statement is true. Increasing the number of neighbors means the algorithm has more calculations to perform. It's like trying to solve a puzzle with more pieces, it takes longer. I disagree. Smaller isn't always better here. Think of it like this: too few neighbors, and you miss important relationships. Too many, and you oversimplify things. The best number depends on your data. Absolutely. The choice of n_neighbors directly influences how well LLE represents your data in lower dimensions. A poor choice could lead to a bad representation. It's a crucial choice. This statement is false. n_neighbors does not control the number of dimensions after the reduction. That's controlled by a different parameter, usually called n_components . It's a separate setting entirely. This is the end of the question, a box which typically summarizes the given problem or a quick recap of the instructions. I'm asking you to identify the correct statements about the n_neighbors parameter within the LLE algorithm. This parameter controls how many neighboring data points the algorithm considers when reconstructing each data point. It's a crucial parameter that directly impacts the performance and accuracy of the LLE dimensionality reduction. Think carefully about how changing this number might affect the algorithm's computational cost and the quality of the final embedding. Let's see how well you understand this important concept. This refers to the n_neighbors parameter used in the locally linear embedding (LLE) algorithm, a dimensionality reduction technique in scikit-learn. I will explain what it does and how changing its value influences LLE's behavior. The abbreviation LLE stands for locally linear embedding. The diagram, not provided here, would visually represent the concept of n_neighbors in LLE. I imagine it would showcase a data point and its surrounding n_neighbors, highlighting the parameter's role in the algorithm's local reconstruction process. It might show how different values of n_neighbors affect the shape of the reconstruction. A picture would be worth 1,000 words here, wouldn't it? I'm looking at the parameter neighbors used in the locally linear embedding algorithm. This parameter controls how many of a data point's closest neighbors we consider when trying to reconstruct that point. Think of it like this: you want to understand a person. You would talk to their close friends, not just strangers. This parameter influences the accuracy and speed of the algorithm. I'm going to evaluate several statements about neighbors to see which ones are true for the LLE algorithm. Each statement will be carefully reviewed. We're looking for the completely true ones. I believe this is true. The more neighbors you consider, the more calculations the algorithm must perform. It's like trying to put together a puzzle with many pieces instead of a few. It takes longer. More neighbors means more computation time. I disagree. Absolutely not. A smaller number of neighbors might miss important relationships in your data, leading to a worse result. It's like only talking to one friend to understand someone. You might get a biased opinion. The best number of neighbors depends on the specific data. I think this is true. The choice of the number of neighbors significantly affects the accuracy of the algorithm. Choosing too few neighbors might cause you to miss important patterns, whereas choosing too many neighbors could over-smooth the data. You need to find the balance that works best. It's crucial to pick carefully. I disagree. neighbors has nothing to do with how many principal components you keep after dimensionality reduction. That's controlled by a different parameter, ncomponents. They're different concepts. Don't confuse these. This question tests your understanding of the n_neighbors parameter in LLE. We'll look at how this parameter affects the algorithm and its results. You need to understand how LLE works. It reconstructs each data point from its neighbors. To get this right, I'll explain the n_neighbors parameter in LLE. This parameter controls how many of a data point's nearest neighbors are used to reconstruct that data point. The algorithm assumes that each data point can be expressed as a linear combination of its neighbors. I agree. The number of neighbors you choose directly affects how well LLE works. Choosing poorly can lead to a bad reconstruction and a less effective dimensionality reduction. It's a crucial parameter to tune. That's not always true. While a smaller number might seem better, it depends entirely on the data. Too few neighbors, and you might not capture the local neighborhood accurately. Too many, and you might oversmooth the data. The best number is often found through trial and error. Nope. The n_neighbors parameter doesn't control the output dimensions. That's controlled by a different parameter. n_components. Think of it like this. n_neighbors focuses on the local neighborhood, while n_components focuses on the final reduced dimension. LLE isn't PCA, principal component analysis, so they're different. Absolutely. More neighbors mean more calculations, so your algorithm will take longer to run. It's a trade-off between accuracy and computation time. We're exploring the n_neighbors parameter in the locally linear embedding algorithm, a technique used to reduce the dimensions of data. Think of it as simplifying complex information. This parameter is really important because it tells the algorithm how many of a data point's closest neighbors to use when trying to understand that data point. I found that increasing the number of neighbors means the algorithm needs to do more calculations for each data point. That's simply because the algorithm has more friends to consider for each data point, thus increasing the computational cost. The number of neighbors you choose greatly affects how well the algorithm does its job of reducing dimensions. Choosing poorly can lead to inaccurate or misleading results. It's like choosing the right number of ingredients for a recipe. Too few, and it might not taste good. Too many, and it can be overwhelming. Experimentation is key to finding the best choice for your specific dataset. I disagree with this statement. Using too few neighbors might not capture the complete picture, potentially leading to errors. It's like only considering a small group of friends to judge a person. You miss a lot of important information. The right number depends heavily on the actual data you're working with. This statement is incorrect because n_neighbors does not control the number of dimensions in the output. The parameter that determines output dimensions is n_components. It's like confusing the number of ingredients in a recipe with the final serving size. This question tests your understanding of the nneightbors parameter in LLE. It's all about how this parameter affects the algorithm's performance and the resulting lower dimensional representation of your data. Think about how the algorithm works, reconstructing each data point from its neighbors. I'm going to say that's false. A smaller nneightbors doesn't guarantee a better result. The best number of neighbors depends heavily on your data. Too few, and you might miss important relationships. Too many, and you might blur the details. It's like trying to find the right balance when baking a cake. Too little of an ingredient and your cake's bland. Too much, and it's a disaster. That's true. Imagine you have to compare each data point to many more neighbors. That takes more time. More neighbors means more calculations, more computation, and thus higher cost. Nope, that's false. nneightbors tells the algorithm how many neighbors to consider when reconstructing each data point. The number of final dimensions you end up with is set by a different parameter. N_components. Absolutely true. The number of neighbors you choose directly affects how well the algorithm can reconstruct the data and ultimately, how good the final, lower dimensional representation will be. It is kind of like a tuning knob. Find the right value, and you get a fantastic result.